During this presentation, I will be showing you the characteristics of the famous Six Flags ride Goliath as if it were a graph, as well as showing you some examples of those very characteristics. And here we go. As you can see here, our slope is beginning to increase. Oh my gosh, we're so high up. Wait a minute. So what exactly does this mean? In the bottom corner, I state that each box equals 10 feet. If you look at my graph, this is the exact replica of the Goliath ride. In the first segment of this graph, the line is increasing to its peak at 165 feet. This means that if there was a Goliath prime, then the line would be above the x-axis. This is because when a graph is increasing, the prime of that graph is in fact above the x-axis, meaning it is positive. So how do I know when the graph is increasing? Simple. First, I'll give you this sample example. It says that f of x equals 3x squared minus 6x plus 10. The first thing you need to do is find f prime. F prime reads 6x minus 6. As soon as you do that, you must make f prime equal to 0 and solve for x. When you solve for x, that will give you your critical number. Now the critical number means where you have a point of interest. This method is called the first derivative test. Once you have found your critical number, create a chart like this. Put f prime over in the right box and put your critical number in the middle line. To the left and right of your critical number, write negative infinity and positive infinity. In the boxes below, choose a number that is really negative and really positive. I decided to choose negative 10 and 10. Plug in that number into your f prime equation. Solve for f prime, and if your number is negative, put a negative at the top. If it's positive, put a positive at the top. When I plugged those two numbers in, I got negative 66 and positive 54. Once you have put your negative and positive at the top, draw an arrow showing whether your graph will be decreasing for negative or increasing for positive. That will show you whether your graph is increasing or decreasing without even having the graph right there. Alright, back to the ride. As the music changes, we begin to meet our absolute maximum. Now before I show you why this maximum is so absolute, let's talk about poi. I should probably tell you what poi is. Poi stands for points of inflection. The point of inflection on a graph is the point where a line is changing from increasing to decreasing. In this sample graph, you can see that I labeled where there are in fact points of inflection. There are 4 types of points of inflection: relative maximum, relative minimum, absolute maximum, and absolute minimum. Like I said before, we are approaching our absolute maximum. Well, I bet you're thinking, so how do I find the absolute maximum on a graph if I'm not given a picture? Whoa, slow down there. I'll tell you about that when we get down to the absolute minimum. Look, we're already declining. Got there faster than you thought, didn't we? If you look back at our original graph, you can see that there is a very top and a very bottom. That is our absolute maximum and our absolute minimum. So back to that question on how exactly do you find the absolute maximum and absolute minimum? I got you. Let's use the same example I gave you before, except we're going to close the graph between 0 and 5. Go ahead and find your critical number using f prime and solve for x. Plug in that critical number into your original equation f of x, and that will give you the y value for that point of inflection. Because this interval is closed, go ahead and plug in those two numbers, 0 and 5, into your original equation. Solve for y, and those will also be two y values for those 2 points of inflection. Where x equals 1, the y value was lowest of the three numbers. That means that you have an absolute minimum at 7, and because at x equals 5, you had the highest y value, you have an absolute minimum at x equals 5. Alright, back to the fun. Now the ride is concave up. Oops, forgot to tell you about concave up. I got you. This is what a concave up and concave down graph looks like. When f of x is concave up or concave down, that determines what f double prime will look like. Because the first part of Goliath is concave down, that means that Goliath double prime would be negative, and the second part of Goliath is concave up. Goliath double prime would be positive. Alright, let's review what we've learned about f of x, f prime of x, and f double prime of x. When f of x is increasing, f prime of x is positive. When f of x is decreasing, f prime of x is negative. When f prime of x is increasing, f double prime of x is positive. When f prime of x is decreasing, f double prime of x is negative. When f of x is concave up, f double prime of x is positive. When f of x is concave down, f double prime of x is negative. And so on and so forth. You could keep going forever with the primes. Okay, I promise I'm done talking for now. And here we are at our relative maximum and our relative minimum. So how do you find your relative extrema? This is an outline of the Goliath ride. As you can see, there are many bumps and hills in the ride, but they're not all the same height, and that is where relative extrema come into play. Luckily, you've already done all the hard work. Do you remember all the work that you did for increasing and decreasing? Well, I hope you didn't throw it away because you don't need to do anything else. Where you drew your line to see whether the graph was increasing or decreasing, just connect it and you will see that you had a relative minimum at the point x equals 1. See? All the hard work is done. Now sit back, relax, and enjoy the rest of the ride.